students, as snow diminish, bare underlying surface like soil, rock are exposed and they start absorbing heat. These uncovered surface absorb significantly more solar radiation, leading to additional warming. This extra absorbed heat accelerates further melting of remaining snow and ice. What is the impact of this? It creates a self-reinforcing positive feedback loop known as the ice albedo feedback. The ice albedo feedback is one of the strongest processes that increases climate warming. Once it starts, it greatly influences the initial heat caused by greenhouse gases. Even an insignificant increase in temperature can trigger extensive reduction in snow and ice cover, resulting in extremely large increase in absorbed solar energy. This feedback describes why temperature changes in polar regions are often greater than the global average. This phenomena, which is known as polar amplification. The Arctic region has evident warming twice more than the global rate in recent decades, largely due to the triggered loss of sea ice and snow cover surface. Ocean ice concentration plays a primarily important role in managing the energy balance of the polar ocean. The snow cover reflects sunlight and acts as an insulating to heat between the relatively warm ocean and the cold atmosphere. Due to the rapid retreating in ocean ice, ocean water absorbs more solar radiation for the duration of the hot summer. Storing heat delays ice forming in winter and leads to formation of thin ice cover. This process increases long-term warming of the polar oceans and stimulates atmospheric circulation, global weather pattern and marine ecosystems. So, now you can very well understand that the cryosphere is a significant regulatory of the global heat energy balance through its high reflectivity and insulation to the heat absorption of the ocean. It plays a critical role in energy exchange with atmospheric and ocean circulation. With changing climate, its regulatory function is declining, this by melting of snow and ice cover, which increases the space of solar energy absorption and amplifying of warming. Comprehending these exchanges is essential for accurate calculation of climatic modeling and effective mitigation strategies that ensure long-term climate stability. Now, let me explain to you the climate change influence on the cryosphere. Data on climate warming over the past century has recorded noticeable changes across all components of the cryosphere. Information collected from various instruments, satellite data and field observatory evidently demonstrate that increase in atmosphere and ocean temperature is largely driven by anthropogenic release of greenhouse gas emission, which are altering frozen environment worldwide. These changes are not responsible alone, but they are a whole process that emphasizes one another and generate tumbling impact on global climate and water resource distribution. Because freezing systems respond promptly to temperature change, the cryosphere has developed as one of the clearest and most sensitive indicator of present climate change. One of the most prominent impacts of warming is glacial retreat and mass ice loss. Glaciers across all mountain regions, including the Himalayas, Andes, Caucasus, Alps, Rockies and East African highlands have evidenced sustained negative ice mass balances in recent decades. Increasing temperature develops surface snow melting, while change in precipitation pattern often reduces the snowfall accumulation, which is limiting glacier replenishment. As a result, glaciers are retreating up a slope. Comprehensively, increased meltwater can raise river discharge and trigger hazards such as glacial lake outburst floods. Over the longer term, however, continued ice loss reduces the buffering capacity of glaciers, threatening dry seasons water available for agriculture and drinking water. The Himalayan cryosphere, also referred as third pole, explains these challenges evidently. As a regional case study, Himalayan glaciers provide a good example how the climate change impacted the cryosphere. As feed major river systems in South Asia such as Indus, Ganga, Brahmaputra and support hundreds of millions of people over the plain regions. Rapid glacier retreat increases flood risk in these rivers and raises a serious concern about long-term water availability to the lower reaches of the river. Similarly, trends are evident in the outer higher lands of Europe and America, where glaciers decline threatens urban water supplies in one hand and retreating glaciers have reshaped landscape and affected tourism and energy production on the other hand. Another key indication of climate change is the rapid decline of Arctic ice sheets. According to the satellite observation since the late 1970s, shows distinct reduction in both sea ice extent and thickness, especially during summer. Huge multi-year ice layers have increasingly been replaced by thinner first year ice that melts more easily and it is very fast in nature. This loss diminishes surface albedo, allowing the dark ocean to absorb more solar radiation and further strengthen warming through positive feedback. While sea ice melts does not directly raise the sea level, it greatly influences atmospheric circulation, ocean and atmospheric heat exchange and also indigenous livelihoods. At the present time, ice sheets in Greenland and Antarctica are losing depth at increasing rates. Surface thawing enhanced ice flow into the ocean. Interaction with warm water is also one of the reasons of accelerated ice discharge into the ocean's water. Parts of these ice sheets may be approaching critically thresholds beyond which ice loss could remain even if temperature remains steady. Such changes pose long-term threat of several meters sea level rise, one of the most concerning aspect of the cryospheric changes due to its non-recoverable on human time scales. Climate change has also reduced snow cover duration, particularly in the northern hemisphere. Earlier thawing of frozen sphere reduces surface albedo, alters river flow discharge and increases the risk of flood in lower reaches and summer water shortages. Environmentally, reduced snow protection affects soil, nutrient cycle, vegetation growth and flora and fauna distribution. Additionally, permafrost melting is accelerating and releasing large amount of carbon dioxide and methane, which further increases the global warming. So, students, now you can understand it very well that overall climate change impacts on the cryosphere are extensive, interconnected and it is irreversible in nature. Glacier reduction, decline in cryospheric mass and permafrost thaw not only signals a warming planet, but also vigorously drive further climatic and socio-economic changes. Attending these impacts is therefore central to gathering the broader challenge of climate change in the 21st century. Now, after explaining to you the interconnection of cryosphere and climate change, let me explain you the cryosphere and sea level rise. This change is one of the most important significant drivers of global sea level rise related to the warming in polar and mountain regions immediately to impact in far coastal areas. Sea level rise occurs through two primary ways. One, by the addition of the fresh water to the ocean from thawing of highlands, ice and the thermal expansion of the seawater as they get warm. As thermal expansion adds substantially, the accelerating loss of ice cover from glacier and ice sheets has become an predominant factor in recent decades. Mountain glaciers, although relatively small in quantity as compared to ice sheets, they have made a disproportionately large contribution to sea level, increasing because of their rapid response to temperature changes. Glaciers in high altitude regions are retreating and thinning at unprecedented rates. Since glaciers respond quickly to warming, their influence to sea level rise is expected to persist in the near future, even if global temperature stabilizes. The most profound long-term risks, however, are linked with the melting of large ice sheets, particularly the Greenland and Antarctic ice sheets. The Greenland ice sheets has appeared as one of the largest suppliers to observed sea level rise due to increased snow melting and greater discharge of ice into the ocean. Meltwater on the ice sheet surface can penetrate deep through crevices, accelerating the movement of ice toward the coast. Antarctica, especially West Antarctica, is also increasingly exposed as warming ocean waters wear down ice shelves from below, reducing their stabilizing effect on inland ice.